Hello everyone, my name is Hao Yuan. I'm so sorry due to the visa issues. It's so pity that I can't be able to attend the HotMobile conference. So I recorded the video, but I will answer questions remotely. It is my great pleasure to present our work. How do mobile apps violate the behavioral policy of advertisement libraries? As we all know, mobile apps are increasingly popular in recent years, and the number of apps in Google Play has surpassed the 3.6 million mark in 2018. And free app is a trend in the Android ecosystem. More than 90% of apps in Google Play are free. Ad libraries are commonly used by app developers to monetize their apps by showing ads to mobile users. Recent research suggests that there are more than 1,000 different ad libraries. Many research work focused on the topic of mobile advertising in various directions. One line of work focused on the ad library detection. For example, Labrada and Wukong use clustering-based approach to detect advertisement libraries. Another line of work focused on the privacy leakage of advertisement libraries. Some work also proposed to separate the privilege of advertisement libraries from the host apps to prevent permission escalation attack. Moreover, several work proposed to detect click fraud of advertisement library in Android apps. To increase economic revenue, some app developers turn to entice mobile users to unexpectedly click ad views during their interaction with the app, resulting in kinds of ad fraud. So to regulate the behaviors of apps that use them, some popular ad libraries such as Admob and DoubleClick have released detailed policies, including how the ads should be placed and how should they interact with users. Google Admob has released a series of policies as shown in the figure, including content policies, behavior policies, and so on. These policies are used to guide and regulate the usage of Admob library. Some policies are mandatory and are meant to avoid kinds of ad fraud, which might affect user experiences significantly. So once an app developer fails to comply with these policies, Admob will disable ad serving or disable his or her Admob account. But Admob does not explicitly provide how they perform policy violation detection. However, no previous work have studied whether mobile apps comply with those guidelines, whether Android apps comply with the usage and behavioral policies defined by ad network. In this work, we propose to study how Android apps violate the behavioral policy of ad library. We choose the Google Admob library as a starting point because it is a quite popular ad network provided by Google, the official maintainer of Android, and it has defined clear guidelines and policies for its user to follow, which uses implementing and checking for instances in which ads violate those guidelines and policies. In this paper, we only focused on behavioral policies of Google Admob. So we first summarize the behavioral policies of Admob into 6 categories. The first policy is about ad placement. The ad view should not be overlapped with or hidden behind other views. The second policy is about the interaction behavior. The ads should not be placed in a location that covers up or hides any area that users have interest in viewing during typical interaction. The third policy is that there must be a way to exit the ad view without clicking the ads. The fourth policy is that the ad views should not be placed in applications that are running in the background of the device or outside the app environment. The fifth policy is that the ad views should not be triggered frequently. For example, the ad views are triggered every time the user clicks within the app. The sixth policy is that the ad views should not be placed on the non-content based pages, such as thank you, error, login, or exit screen pages. So we propose a four-step approach to detect the policy violation apps. The first step is to identify apps that use Admob library. In this work, we use LabRadar, an obfuscation resilient approach to detect apps that use Admob library. LabRadar is our previous work, which has mentioned the good features of more than 5,000 third-party libraries. Then we propose an automated test input generation technique to run apps that embed the Admob library on smartphones. And we generated the UI transition graph. Note that we preserve the attribute information of visual views and the state transition information in the UI state transition graph. So the third step is to identify ad views from the UI state. By leveraging properties such as the resource string, view tabs preserved in the attribute information, we can identify Admob ad views accurately. Finally, we apply a set of heuristic rules to detect policy violations. As we all know, Monkey is the most popular and lightweight tool to perform Android GUI testing. But the inputs generated by Monkey are completely random, which is not effective for us to explore the ad content states and generate the UI transition graph. So in our approach, we generate the inputs based on the current UI state to simulate real user behaviors. We take advantage of accessibility to understand the layout of the UI state and obtain the information from each view, such as the name, a stat, and the class name. This information could be used to build a view tree that can accurately describe current state. Our automation technique gets the view list from the current state and choose the event input for the next view. Previous work suggested that traversing all the UI state of an app takes several hours. So by manually labeling roughly 2,000 UI states that generated from 180 apps, we found that roughly 90% of the UI states do not contain any ad view, and more than 90% of the ad views are displayed in either the main UI state or exit state. So we take a breadth-first traversal exploration strategy. We explore each state with 50 events, and the initial experiments on 180 apps suggested that the time efficiency increased by 17 times on average, and we could cover 90% of the US states that contain ad views. To detect policy violation apps, we first need to locate the ad views from the US state transition graph. So one challenge here is how to differentiate the Admob ad views from a large number of normal views in a given US state. So we randomly select 180 apps and manually labeled roughly 2,000 generated US states, in which roughly 200 states contain ads. We then compare them from various aspects to explore features that can distinguish them. We found that roughly 90% of Admob ad views have special representative strings in the resource ID field. For example, usually the resource ID contains strings such as ad view, ad web view, ad layout, ad container, full screen ad view, and so on. These features could be used to identify the ad views accurately. For apps that have no explicit string features due to fully obfuscation, we use a heuristic detection method based on the type and the position of the view. For example, we found that all the Admob ad views are implemented by system views, image view, and web view, and these views usually have a specific size and positions. So we use these features to help us identify the ad views. We now provide the practical rules that are implemented in our work to detect violations. For the violation number 1, the key behavior is that the ad views are overlapped with or hidden behind other views. Thus, we calculate the size, bounds, and the coordinates in the attribute information of the views to detect overlap and hiding behavior. The red figure shows an example of violation 1 that we found in Google Play. This app has more than 1 million downloads. It's clear to see that the game button is overlapped with the ad view, which could cause accidentally click. For the violation number 2, the key behavior is that the apps display ad views during users' interaction with the app. So our strategy is to identify ad views that are placed on top of interactive views. So we first identify the states that contain interactive views, such as dialogue and buttons. Then we check the adjacent UI states to analyze whether an ad view exists. The UI states will be regarded as violation if an ad view is placed on top of interactive views. So the red figure shows an example of violation 2, and we found in Google Play. The ad view pops up above the instruction dialog during user's interaction. For the violation number 3, the key behavior is that the ads can't be closed unless clicked. So in general, the interstitial ads and full screen ads could be closed by either clicking the closed widgets or touching the back button. Since it is non-trivial to automatically identify the closed widgets, so in this work we only consider the situation where interstitial or full screen ads can't be closed by touching the back button. However, we did not find this kind of violation in our experiment. One possible reason is that this kind of violation could greatly decrease user experience, which will lead to the uninstallation of the app. So this type of violation is uncommon. For the violation number 4, the key behavior is that the ad views are displayed outside the host app. So our strategy is to identify ad views that are displayed after its host app exists. Note that the host app of an ad view will be system default home app if the tested app exists. So for each state that contains ad views, we check the package name of the host app to see whether it is the home app. The red figure shows an example of violation 4. We can see that the ad view is placed on top of the home screen after exiting the host app. The violation 5 is flagged if and only if an ad state is triggered more than 3 times. To avoid repeated visits, which may cause inaccurate counts, we only count it only once if a UI state is visited, although multiple times via the same path. The figure shows an example that we found in Google Play. This app has more than 1 million downloads. We can see that the ad view triggers every time after the main activity receives an event input. The violation 6 is flagged if and only if the interstitial of both screen ads are placed on the app launching, exiting, and login pages. The app launching and exiting states could be identified when we start or close the app. The login state can be heuristically identified based on the view information. For example, if a state contains 2 edited views, and it has string features such as username and password, we will regard it as a login state. The figure shows an example of violation 6 we found in Google Play. We can see that the ad view is placed on top of the launch screen page. Our experiment is based on roughly 6,000 apps that crawled from Google Play, in which roughly 60% of them use Admob library. we then get roughly 39,000 US states, among which 3,800 states contain ad views. We manually labeled the ground truth data. There are 89 apps in our dataset violate the behavior policies, and our detector could achieve an accuracy of 86%. The distribution of the 89 policy violation apps is shown in the red figure. Some apps have violated more than one policy. More than 97% of the policy violation apps breaks the policy 6. That is to say, these apps pops up as upon launching or before potentially leaving the app. One possible reason is that placing ads on these pages could potentially increase the impression and clicks. Okay, for the conclusion and the takeaway messages, in this work, we found that the behavior policy violation is indeed a real issue in the Android ecosystem, and roughly 2.5% of the apps in our experiment have violated the Admob policies. So we think the app market and networks should take efforts to identify and prevent policy violation apps. Moreover, and the network should also consider how to prevent or check certain policy violations when designing the advertisement libraries. We have released the dataset and experiment results to the mobile app research community as the GitHub repo, so you can scan the QR code to access the page. Thanks for your attention. I'm ready to answer questions remotely.